Good afternoon, everyone. Can you hear me? Yeah, great. Okay. So thank you for joining me for this lovely afternoon. Not very warm in London, but nothing is actually very warm in London, maybe for 2 weeks. So welcome to my presentation about layers in TensorFlow. Out of curiosity, who has ever here worked with TensorFlow? Okay, more and more people every time I give a talk on TensorFlow. Who has ever worked with deep learning? Okay. Who has came here because there is this big hype and you want to keep up to date for machine learning? And yes, of course. So you're in a good place, but this is not like a very introductory talk, and I will tell you how this is actually not a bad thing for you. So who am I to talk to you about this? I'm a programmer. I have been a programmer for over 13 years, maybe 14 this time because we have a new year, so I can count it for a new year. My background is in machine learning also because I wrote my master's degree dissertation in machine learning, but it was so long time ago, it wasn't called machine learning, it was called data mining. And then I was doing my PhD dissertation also on that topic. At the moment, I'm a data science freelancer. I'm ex-Microsoft. I'm joining Google in like 3 weeks. So I will stop being freelancer anymore, and I will be a machine learning engineer. So because it's not actually the introductory talk, I have a good news for you. All of my examples, instead of you going to my GitHub account and trying to download the examples, which you would never do, I will point you out to this amazing platform that is called Katacoda, and you have fully installed, set up environment. You can run the code there. It's like a shell in a browser, and you don't have to install anything. So all of the demos I'll be showing you today are there. If there is anything unclear, if there is something I couldn't, because of the lack of time, explain to you, it will be there. So what we are going to talk today about, what am I going to talk today? My favorite topic, which is machine learning, deep learning, in particular because we are talking about TensorFlow. And then I will tell you a little bit about how neural networks are built. And I've put a layered cake here. So this is an indication that we'll be talking about layers. So I won't be focusing on the training phase. I won't be focusing on the TensorFlow syntax. I'll be showing you how to use TensorFlow to build layers in our neural networks. And I will be showing that to you to solve the task of classification, and we'll be using this dataset. If you don't know what it is, I will introduce it in a second. And then I will go straight to Katacoda and to the code, and we'll be showing you how to build your network deeper and deeper. So we will go from 1 layer to 5, maybe 6, depending how you define the layer. So what's deep learning? Who is brave enough to tell me what's deep learning? Come on, don't be shy. Yeah?
I heard it said it's using a network with more than one hidden layer.
So deep learning is some kind of like machine learning that is using neural networks with more than 1 layer. Depending on the book, article, or website, the number of layers differ. Of course, yes? You, sir?
It's unsupervised learning, so you just chuck it a whole bunch of information, get it to figure stuff out by itself, as opposed to
supervised learning.
Yeah.
So you're saying it's unsupervised learning as opposed to this supervised learning. Actually, it can be used for both supervised and unsupervised learning, but the cool stuff that is happening that you can read in the headlines are actually in the area of unsupervised learning. So all of the generation codes, all of those cool tweaks that you put your picture there and put some Picasso paintings there and say, change my picture in this style, this is all unsupervised learning. But it has a supervised element too inside. But yes, of course. Anyone else? Okay, so my favorite answer, I agree with you, those answers are very good, but my favorite answer for deep learning was it's matrix multiplication. And if you know a little bit about linear algebra and deep learning, you will appreciate the joke. If you don't yet, I will try to explain it. I know it's not a good thing to explain a joke once you told it, but that's kind of point of this presentation. So deep learning for me is something, it's a tool. I'll give you a second to read both texts and both on the t-shirt, it's also very nice. So for me, deep learning is a tool that gives us now the opportunity to feel like magicians, not magicians, wizards or witches in my case. But we have gender now, so I can say wizards. We are now actually living in the future. The stuff that were in sci-fi movies that were impossible a few years back, deep learning, neural networks, are giving us the chance to actually do them. And don't get me wrong, I know it's all maths, sometimes very complex, and but it's very down to earth when you look at those deep networks. But the result, the stuff that you can see, what those headlines are like hitting, those are incredible. I personally feel like Hermione sometimes when I know the right comment, when I know the right algorithm to use and solve the problem. So I think we are in a stage that we can say our technology is undistinguishable from magic. So what are those neural networks? Where did they come from? What they are? So the idea, like decades ago, was to mimic our brain. So our brain works amazingly, and we can achieve amazing stuff. So someone thought, not just one person, a few people thought, why don't we just figure out how does it work, put it in a machine. Machines are better in calculating, they are faster, so we will create something that will be an artificial intelligence. And there was one problem with that. Nobody knows how human brain works. So we knew a few things. We knew that our brain has neurons, right? We have cells that are called neurons. We know those neurons are connected, and we know they are like passing the impulses to achieve something. So nerves, neurons, intelligence, but that's basically what we know. If you know more on this, in this area, if you're like neurologist or a person that is interested, of course we know much more about how human brain works. But when you think of deep learning and neural networks as the technology that is mimicking our brain, that's basically it. We took a concept of a neuron, we took a concept of neurons being connected, and we took the concept of passing signals. That's all what it is in artificial neural networks. Nothing else from human brains basically taken. There is the concept of layers, of course, but from what I read recently, there are layers in our brain, but they're not as straightforward, as distinguished as they are in the artificial neural networks. So, well, yeah, it has to be obligatory. Some of you are probably too young to remember this, this movie, but this is how my title came in. So basically, neural networks and deep learning is based on layers. The deeper a network gets, the better results you're getting. The downside is it really increases the time that your network is being trained, but the result is worth it. So layers in artificial neural networks. This is a very simple artificial neural network. It only contains fully connected layers. What does it mean? We have, those layers are put here. We have 4 of them. Although some people are saying that input nodes are not actual layer, depending where you read, depending on the tool you're using. And what makes the network deep are actually hidden layers. So let's start from the beginning. We have some inputs, let's say the image. We have some outputs. This is what our network is trying to figure out. And we have hidden layers. This is a very bad name, by the way, I mean, in my opinion, because those hidden layers are not really hidden. You can touch them, you can see what's there. And the whole magic is actually happening in those hidden layers. So you can increase the number of cells in your layers, but the real complexity is introduced, and your network will perform better if you increase the numbers of layers. And this is where the whole fun starts. So let's look closely. What is happening in a single cell? So let's look at this cell. this cell is connected to all of the cells from the previous layer. And this cell is storing weight for all those inputs. So it's taking all those inputs, multiplying them by weights, and then aggregating the results, usually by summation. And then it goes through something that is called activation function. This is not a very complicated maths, right? It's multiplying, adding, and applying a function. A function can be complicated, but as programmers, we know all those libraries have them already implemented, so you just wrap it up with the function, and you're done. If you know anything about linear algebra, this is the explanation of my joke about matrix multiplication. This is matrix multiplication. Multiplying, adding, and putting in the right place in an output. So for every layer, we have a matrix that is storing the weights for every cell. So we have a matrix. Input layer contains a vector, and then we are multiplying it, and this is basically what those calculations are. I know if you're not a mathematician in your heart, it's not very funny anymore, but yeah, I find it funny. So this is fully connected layers. This is like the basics, the foundation of how the maths work in deep learning and artificial neural networks. But the story of artificial brain starts in the 40s. So you can see there were first like gates, electronical gates. And they were trying to figure out the weights, how to teach, how to make them learn to adjust. And then when we go through 50s, 70s, and then we have this first-time perceptron, 57, multi-layered with backpropagation, the algorithm that is used for training till now, still, 86. Then there was this hype of SVM machines. So everyone that was working in machine learning and data science till very recently, like 5 years ago, was doing SVMs. And then there was deep neural network. And basically, if you think of principles, if you think of the foundations, nothing really changed. And now there is this big hype. Now we can do miracles. Now we live in the future. Now our technology is indistinguishable from magic. What happened? What changed? Before I will tell you what, or you will tell me what, I'll just tell you like somewhere here in 2005, when I was picking up my PhD dissertation, and I had this talk with my mentor, and we were thinking, what to do next with this data mining thing? And I said, well, this is amazing what those neural networks can do. You're just adding, multiplying stuff, and it can do miracles. And he said, well, nobody's using it. It's not going anywhere. It's a very niche project. It's purely academic. So we decided I will deal with evolutionary algorithms, which is now nobody's using it. It's a very, very niche project and very academical. So what changed? Why now? Why we have all those neural networks now actually doing things? It's not like it's purely academic. It's actually in production. We are all interacting with it one way or the other. So what changed?
Commodity hardware.
We have hardware, right? We have technology.
Hardware.
Yeah.
The ability to cluster commodity hardware.
Yes, so we have hardware, but we don't have to buy hardware, right? We have cloud. The cloud has better hardware. We have hardware that can do matrix multiplication better, right? We have GPUs, TPUs. What else changed?
Data.
We have data with actual big data. It's not like data that doesn't fit into your memory. It's an actual data. Every company is storing the data. What else changed?
Slabs.
Yeah, I know. But it's very vague. I did it on purpose. We have tools, right? There is this whole concept now of democratizing AI, and it's not just, it is also for headlines, of course, and for getting grants. But if you want, you can do AI, like everyone can. Probably the first try, it won't be great, but you will be doing it. So it's out there for you to reach, right? And in my opinion, it's because people actually proved it works. So they proved that you can solve the most complex task in computer vision. Do you know what's the most complex task in computer vision? distinguishing between cats and dogs. Nobody could do it before. Now we have deep learning, now we can do it. Now it's a solved problem. And like a few years ago, it wasn't. People were trying to put algorithms like this cat has pointy ears. Oh, dogs also have pointy ears, right? And you try to describe it in deterministic rules and algorithms, and now you just feed your network with examples, you label it, boom, you have cats and dogs. Sometimes dogs, like Chihuahua dogs, are mixed with cupcakes that has lots, but yeah, it's also, I think it's now the unsolved computer vision problem still. So there is this great TED Talk, I encourage you to watch it, about the research facility that was doing this amazing new technology, innovative thing. Was trying to teach computer to recognize images like we teach kids, or like kids are learning from observing the world. And like when kid goes to she's telling the story, when kids go to the park, sometimes parents are saying this is a cat, this is the tree, but most of the times they are not. So they were trying to teach the machine, teach the algorithm, teach the model how to understand images. And they succeeded. Now it's normal. Now we know that this is the way to go. But back then, it was a very innovative, revolutionary idea, and they succeeded. And another thing is, we have no tools. Tools like TensorFlow. TensorFlow is not the only one, by the way, but it's surely the most popular at the moment. So if you're doing deep learning, at least when you started recently, you probably got in touch with TensorFlow. TensorFlow works in a way that you're building a computational graph, and then you're feeding your data into it once you want to do the computations. I will show you that in a second. TensorFlow gives you a lot of APIs, libraries, classes on different levels of abstraction. So if you want to just say, build me a network that has 3 or 5 fully connected layers, you can do just this, or you can go deep down and create your own algorithms from scratch. Let's go to our classification task. If you haven't encountered this, MNIST dataset is a very well-known machine learning dataset. Before there was deep learning, computer vision algorithms were trying to solve it because it's very simple, but understandable and quite production kind of wise dataset. So there is a dataset that has handwritten digits, and the task is to recognize the digit. Very straightforward. Don't be fooled. Those are not numbers. Those are digits. So this is a classification task. Those are labels. Those are categories, not numbers. We're not calculating this number based on those pixels. We are recognizing it. It's a different task. So every image is fed. Well, every image. Every image from the training data set is fed through our neural network. The networks goes through training, and then it's ready to recognize new examples. Every digit in this particular data set, there are a few of them, but in this one, is in grayscale, and it's 28 by 28 pixels. And what you usually do as your first attempt, or what people usually did in their first attempts, at least when there weren't deep learning, they were flattening it. So in our first attempt, we'll flatten this file. So we will get 784 pixels, 784 numbers, basically. This will be a number between 0 and 1, I think, which will indicate how close it is to white or black. And another concept, which is introduced in many tutorials very early, is something that is called is batches concept. So in classical machine learning, when you're training your algorithm, you're usually using all your training data. So you take all your data, you train your model with all of them, and you repeat the process most of the times. With deep learning, it's rarely the case, mostly because we use deep learning for actual big data. Like we have tons of examples. So one thing could be we cannot even load the whole data set into our memory. That could be one thing. Another thing is it would slow down the process massively. So if you're thinking like our MNIST data set, I think it has 60,000 examples in the trained data set. Every time we're loading everything and putting it through our model, this will slow down stuff. But that's only the reason why people started to look for new solutions. And batches were actually proven to work almost as good as the whole thing, or even better. So one iteration using one batch, another iteration using another batch, and it speeds down the process. Like the speed is going very well, and the accuracy stays the same. So there are a few algorithms like gradient descent, stochastic gradient descent, and batches approach that will give you the opportunity to fit in this hyperparameter than the size of the batch. So this is a decision you have to do when you're creating your algorithm. So once we have our process trained, during this process we are adjusting the parameters. The parameters are the weights, the things that we are multiplying our inputs with. So those are things that has to be adjusted. That's the whole point of the training process. Once we have them, we can then use it to classify new examples. So then you can draw a digit, put it into grayscale. It can go through your neural network, and boom, it should work. First attempt, what we'll do, I would do, and you can do it on Katacoda later, is I'll build a neural network that has 2 layers or just 1 layer, depending on the definition. So input layer and output layer, that's it, no hidden layers. So we have 784 cells in the input and 10 cells, 10 neurons in the output layer. So basically we're taking our image, flattening it, putting it through the output. Once the weights are trained and adjusted, it's using a softmax algorithm to figure out which cell activated the best, and we have our answer. So I will show you a demo now. So if you go to Katacoda, and to my profile, and it's called TensorFlow layers, or layers in TensorFlow. I will make it a little bit bigger. Most of the stuff I was saying, they will be here in this tutorial, but what I will show you is the code, basically. So what I will show you is this thing. So first of all, before we will build the network, I'll show you very quickly how the training process looks like. And I won't go into details, just for you to know what is happening underneath. And if you have a better idea for the training process, and a hint, there is a better idea, I just made it very simple, so not to go into details, you can change it if you want. So it's all fully like you go to this code, you change it, you run it, and it will be there for you. So first of all, I wrote, the code is in Python. I wrote a function that is just reading NIST data set. TensorFlow gives you the capabilities of reading the NIST data set out of the box, so you don't have to do it yourself. You can, but there is no need. And then I'm building the training phase. Actually, I'm building something that is called a computational graph, which I've mentioned a little bit. And computational graph is like a recipe of this is how I want my computation to be performed. And once you've built it, then you run it. But first, I will build it. So what I'm doing is I'm defining a loss function. For those of you who are new to machine learning, this is something that we'll be minimizing or maximizing, because machine learning process is basically optimization process. And you cannot actually mix it up with accuracy. Because with loss function, we want to minimize it. With accuracy, we hope minimizing the loss function will increase our accuracy. So those are not the same function, but they are trying to like get the same goal. So our loss function, not to go into many details, there are links in Katacoda if you're interested, is using softmax cross-entropy algorithm. So basically it's trying to minimize the difference between what our neural network is giving us as the output and what are the right answers. It's trying to like see the difference and minimize the difference between them. And my training step is very simple. This is actually like one of my favorite things in TensorFlow. I'm just saying, you know, Adam optimizer, take my loss function and minimize it. And that's it. I don't have to think how to implement my gradient descent, stochastic gradient descent, or the Adam optimizer. I can just say optimize it, minimize it. Another thing I want to do is I want to calculate the accuracy. So like every few steps, I want to see how my network is performing. At the end, I want to check it on the test data, the data that wasn't visible there during the training phase. So this is accuracy calculations. And this is when I run all of it. So I start an interactive session to run your calculations, to run your computation graph. You have to start the session. And then I'm using number of steps. The default is 1,000, so I'm running 1,000 of steps. And I'm getting batches. So I'm getting batches using the function that is called next batch, also provided by the TensorFlow. And then I'm saying, take this batch and take the labels of this batch and use it. Every 100 steps, I'm calculating the accuracy. And at the end of the iteration, I'm running the train step. So I'm saying, train step, this optimization process here, run it. Run it using the batch data. You can see that I filled it in with the batch data. So in every step, I'm using a separate batch. And that's basically it. And then I'm using it for validation and test data set. So let's run it. Python. No, I won't run it because I didn't show my network. So let's see how do I build my network. So the one-layer network, input and output. So I read this data set and I said my image size is 28, label size is 10 because we have 10 digits, 10 labels in the output. And I'm defining two placeholders. Placeholders in TensorFlow are the places that you're feeding your data when you're running your computational graph. So in our case, this will be the batch stuff, the batch inputs and the batch labels. So at the moment, when I'm defining my graph, we don't know what are the values. We're just saying those values will be of this shape, of this type, and this is how we create it. So I'm just saying there will be a batch. We don't know what size of the batch would be. It will have 748 shape. And the output labels will be of the size 10 because we're using one hot vector. So for every label, there will be one in a place when the label is. This is the boring stuff. The nice stuff is that I just defined now here my whole network, my one layer and one line. And this is why I love the TF layers package or module. I'm just saying, build me a dense network, which is the name of fully connected layer. Use inputs as x input as inputs. So this is the placeholder I defined previously. And use label size. So I will have only 10 cells in my output network. And then I'm using what I've shown you in a help file. So build training and train it. So I'm building the training computational graph, and then I'm building, and then running it. So let's run it. Dense Pi. So it's downloading this data set, and you can see in the file system that there is a folder that it downloaded it. And then it ran pretty quickly, but the accuracy is 83%. Not great. It's not horrible, but not great. So how can we make it better? We'll just put not now. How can we make it better? How can we make it better? More layers, yes. That's the point of this talk, because I was talking too much about deep learning. Now let's go for layers. So we'll add some hidden layers. At least we will add one. You can play and add more if you want, but you will get the gist. With the hidden layers, especially for kind of like computer vision stuff, you have to think of the activation function. So it's not just matrix multiplication. I lied to you. So it's matrix multiplication. We're taking weights, multiplying by inputs, and then we're adding bias, and then we're wrapping it into activation function. And there is, it's another hyperparameter, which kind of an activation function you will use for your layer. So there is a softmax function, there is a sigmoid function, this one, hyperbolic tangent, and they have the green and the blue. They have problem. The problem is called vanishing gradient descent. So basically the backpropagation, the way how the network is trained, is based on derivatives. And if you know a little bit about derivatives, you can guess that derivative here will be kind of like zero, not kind of exactly zero, we're very close to zero, and our computers are great and magical, but they still are rounding up to zero, small numbers, right? So derivative will be zero, here and here. So the network will stop passing their signals, and yeah, there is a problem. So sometimes it's better to use other activation functions. So very popular one recently, and like I still cannot get my mind for the maths because it's very simple. The ReLU function, it gets zero for everything that is smaller than zero, and it's a linear function for everything that is more than zero. And for me, it's basically a linear function, so I don't know how does it work exactly, but it does work. So activation functions are necessity for deep neural networks, and this is what we are going to use. We'll use the ReLU function. So we have our input layer, this didn't change. We have our output layer, this didn't change. But now we're putting one in the middle. So what we have to change is, this one is no longer connected to the other one. It's connected here, and the output is fed by the hidden layer. What size of hidden layer should we use? Well, nobody knows. This is another hyperparameter that you have to think of, try it out, experiment, see what works, or just, look at other people's work and see what are their conclusions, and of course, then you can use it. So I'll show you how to build your hidden layer now. It will be a fully connected layer, so the code should be enough for you to already know that. So the file is called ReLU. So everything stays the same at the beginning. I just added hidden layer size, which I've put for a very round number, 1024. Placeholders are the same, and the first layer is now hidden. So, it's not hidden, I just called it hidden. It's still dense layer, and it gets an input, as an input the placeholder, and I'm putting hidden size as a unit, and there is something more. So if you compare it to the code of the output layer, we have this activation function now, right? If you don't specify activation in your function, it will just take the linear function as an activation function, which means basically not applying any function at all because it's just passing the output of your layer. So this is how easy it is. One thing, I'm just connecting input with the hidden, and then hidden is connected to the output. Pretty straightforward. If you want to do matrix multiplication, TensorFlow allows you to do it. You can always do that, of course. It's just once you're doing it for like 10th time, maybe 5th, you get bored and you're thinking like, I already know that, I got this. Give me some API or some function to do it for me because I get the concept. But I encourage you to do it if you haven't. And the rest stays exactly the same. So remember how quickly the first one ran. Let's see how quick this one will go. Dense ReLU. It's still quick, but it's not as quick. And why is that? because we have now 1,424 cells that store, every of the cells stores 784 weights for the previous layer. So we had 1,024 times 784 weights to adjust. It's not about just storing, it's not a big number, but you have to think of all the batches, 60,000 examples, and adjusting it. Yes?
Are there any parameters within the activation function, sort of whether it's a threshold or gradient or whatever? And if so, are they also trained or are they predefined?
So in this, I think it's predefined because if you think of activation function, you could think of it as another layer, of course. So if it's here, it's straightforward, just pointer to this function, or whatever it works, you probably know better. It's probably like a pointer to the function that is just being applied to every single cell in the layer. But yeah, I cannot tell like 100%. So yeah, we have now a hidden layer there. And it worked. Oh, did we look at the accuracy? It is better, right? 94. That's kind of like, okay, we could live with that, but we can do better, I tell you, we can do better. And what we can do better with it is actually adding something that is called convolutional layer. And this is where the whole fun, where the whole magic actually started working with computer vision tasks. Convolutional layers were known, I think, in the 60s. It's still nothing new to the tech world. It's just somebody took it, applied it, and we actually learned how to train the convolutional neural network. So convolution as a mathematical operator is something that gets the part of the input, doesn't have to be the image, but it's part of the input, and applies the same, let's say, calculation, the matrix multiplication. So we're applying weights, we're adding it, adding bias, and putting it as the output. So somebody took this idea and applied it to neural networks. And we gain few things from that. First of all, fully connected layer, 1,024 times 748, a lot of weights for fully connected layer. If your hidden layers grow in size, you have a lot of parameters, a lot of weights and biases to train. With convolutional neural networks, you're sharing weights. So this operation that is applied to the part of the image is sharing those weights. Those weights are adjusted in all those steps, but they stay the same. And second of all, those convolutional neural networks make your network smaller, make your layers smaller, but deeper. And this depth that was introduced actually shown that it can recognize some interesting things. So like with image recognition, it can recognize the borders. It can recognize the shapes. And far away you're in your network, it can recognize the eye, the nose, and then the whole face. So how it usually works is you're getting your convolutional neural network and you stack those convolutional neural layer and stack it on top of each other. Then you follow up with few fully connected layer. And this is how the basic convolutional neural networks work. It's not just it. There is usually something that is called polling. And polling is an operation that gets works on part of your image and gets, for example, a maximum value or an average value. So you can see like the green rectangle is taking 21, the next one goes and it's 12, then it's 18 and 10. What has been proven is it decreases the size of your network. So you save a lot of space, while it still keeps all the values. You're not losing anything, or you're losing not a significant amount of information. So this is an operation that's usually stuck next to convolutional layer. So you usually have in computer vision neural networks like convolutional layer, polling layer, convolutional layer, polling layer, etc. And then few of the fully connected layers. So I will show you how to build it. There's one trick, actually two tricks. So convolutional layer works on the 2D, 3D images. I mean, it can work on 1D. Convolution can just go through your vector and take parts of the vectors. But why it actually has proven to work for computer vision stuff is it takes your part of your image, and now your image matters. I mean, the place where your pixel is matters. Previously, when we flattened it, the 10th or 700th pixel doesn't matter. We could basically mix them up. As long as we keep the order, we don't care about where your pixel was. Now, we take advantage of what are the neighbors of my pixel. So we're actually reading the image, right? Not just treating it as numbers. So that's a very, very nice way to think about convolution. So our input that has been flattened, we now have to put it back into 2D. And after our convolutional and polling layer, we'll have to flatten it back because then there is this hidden layer that is fully connected and only takes 1D things. So let's go to the demo, and I will show you how to build a convolutional layer. I'll actually run it now because it takes some time. So you can see now that it's actually taking some time. We not only added another layer, we added convolutional layer. So image size, label size, hidden size all stays the same, placeholders. And now I'm reshaping the input. So TensorFlow reshape function is very, very useful one. You would use it all the time, basically. So first, I'm creating convolutional neural network, convolutional layer. And again, I'm using a package, TF layers. I'm using convolution conv2D. And I'm saying, get my input, the one that I reshaped to 2D, use 32 filters, the depth size, use the window 5 by 5, my convolutional window, and you don't actually define the strides here. You're saying, use the padding that is same, which means the output of this convolution will be of the same size as the input. So 28 by 28. And then use activation function that is relu. You could add some bias here. I didn't do it for the sake of clarity, but you could. Yeah. And then I'm using a polling layer. And in my opinion, polling layer is not a layer. It doesn't store any weights. It doesn't store any biases. It does not adjust any parameters. It's not the layer that is being trained. It's just an operator that goes through some input and performs some calculations. But it can be applied to anything you want, and that's probably why the authors of the package put it as a separate layer, which kind of makes sense. So I'm using the polling. I'm using the convolutional layer as an input. I'm saying use 2 by 2 and use strides 2. That's a common practice. That's the first thing you should try. If it doesn't work, then you can play around, but that's usually how it's done. And then I'm flattening this polling output, and again using the TensorFlow reshape function. And this is a very good calculating example. Why do I have 14 by 14 by 32? We'll leave you this as an homework. I actually encourage you to build your own convolutional layers with all the weights and biases and like build it from scratch. I just wanted to show you how, once you understand how does it work, once you understand how to use it, how you can take advantage of some APIs, some abstractions that libraries like TensorFlow offer you. And then I have my hidden layer that I get my flattened stuff. Nothing changes after this. So you've noticed that it slowed down the process like dramatically, but we have better accuracy, right? 97. Basically, we cannot go that further if we just use convolutional and fully connected layer. We probably could go to like 99, and we'll try to do it. So you could try to do it. Let's just add more layers, and it should speed it up. But like in general, when we talk about accuracy, 100 is the farthest it can go, right? it usually takes you the same time to go from 40% to 70%, or like 80 or even 90%, and then like every percent is a win after that, right? So what I will show you, just very quickly going to slides, is, oh, I just came back, is how to add another convolutional layer. And you can use this, if you want, to just add another. All you have to do is just put another, put it as 2D, and flatten the last layer to feed it into the fully connected layers.
And would each of those convolution layers have a sort of post-processing pooling layer as well?
Yes, yes. So in my examples, they don't have to. Like, actually, like, you probably have seen so many headlines about those cool things that machines can dream and generate the images. So they're using the convolutional layers and polling layers, like, also for this. Because it's playing with the sizes, it's sometimes mixing up, so it's a machine type of innovation and creativity, I would say even. And there are some articles that say that actually polling layer, which is very popular with computer vision tasks, is not doing a good job with generating images. So generating images, it leaves you with rectangles there, because it's getting like average or max pol and passing it as the output. So as the result, sometimes if you like zoom it, you can see all those small rectangles, so it's not that great. So there are new techniques now you could replace the polling with, but yeah, the classical convolutional networks are usually the pairs of convolution, polling, convolution, polling, convolution, polling, and at the end, the fully connected layers. So again, I will run it, because now it will be very slow. Python to convpy, and we'll look at the code. Nothing changed, reshaping the image, and first convolutional, the same. 32 filters, 5x5 window, padding the same, activation function, relu. Polling layer, 2x2 strides. And then I just use the polling layer as the input to my second convolution. I don't have to reshape it now, because now it's 2D. Actually, it's 3D, because we have the same size and we have depth, so we have now 3D. It takes some time for people like with soul imagination like mine to go through the fact that this input is 3D and we have 2D convolution. Like, how does it work? It's actually applying 2D convolution to every piece of your depth. But I'm not here to teach you about convolution. This is quite a complex topic. I recommend to take some course if you really want to understand it. It's worth understanding, and there are plenty of resources out there. So just Google it. So my second convolutional layer, I said I want 64 filters. So now I want to do 64 depth. My kernel size is still 5x5, and I have padding the same. Then I'm using polling layer, and then I have 7x7x64. Like, seriously, it took me like 2 hours of a headache to come up. Why? Why is it? I knew it was working because I checked it, but yeah. By the way, most of the problems that you will have with TensorFlow, and basically deep learning doesn't have to be TensorFlow, any deep learning library would be that you mixed up the dimensions of your tensors. So if you mixed it up, you can always use something like reshape or stuff that will squeeze or spread your things, and it probably would work. But this is the thing that you have to think of at first when something is going wrong. So we have 2 convolutional layers. You get the gist, how to add another and another and another. Now you just have to think of this size when you're flattening it at the end. But there are also equations out there that will help you figure this out. Then I'm flattening it, then I'm feeding it to the hidden layer, rest stays the same. And I've been blabbing for a few minutes now, and it's only on step 600. So yeah, let's have a, we'll have a wait, maybe not for the moment. I will be telling you other stuff in a second, and we'll go back and see how does it perform. So let's leave it like this. So yeah, convolutional neural networks, pretty basic and starting to be complex topic. So I found like fully connected layers in every introductory course, training, tutorial. It's pretty simple to grasp, especially when it's so easy to implement. Convolutional neural networks, even though they have been there for 40, 50 years, they start to like, maybe not you, maybe you're smarter than me, but they started giving me a headache once I started learning about them. So the idea I got, like 2D, we're taking advantage of the pixels that are near to each other. I get the depth, I've seen it. I look at the hidden layers, and I've seen all those edges recognitions, all those noses, eyes, etc. You can see that, and you can feel it's working. It's just like, now it starts to be complex. Now it's all this reaching out there, democratizing of AI actually demands something from you. You have to learn, you have to understand something, you have to code something. You have to know when to use this kind of a network for those kind of problems. And don't get me wrong, learn deep learning and go out there and see what's out there. But this is pretty basic stuff. And if you haven't know this topic, unless I'm a great teacher that I just taught you all about this, you probably don't get it fully at the moment, right? So, or at all, as I can see in the audience. So this is when it starts to be a learning process. This is when it's like, well, I thought this TensorFlow thing would just like, I would just like say, recognize the digit, and it will, right? It will just figure out which network I need, what do I have to train. And I thought this will be this easy. And it is easy, and it's easier. It just doesn't mean you don't have to learn, experiment, because you do. It's called data science for a reason. Okay. The last concept, the last layer I would like to add to our network is something that's called dropout. So I've read in many books that dropout should be only added to fully connected layers, which is not true, basically. But I will explain it to you on fully connected layer. So there is this thing called overfitting. Overfitting is a glorified name for your model, not just neural network, to learn examples by heart. And while it's overfitting, it has a hard time to recognize examples it hasn't seen during the training phase. So it learned so well on those examples and it limited itself. So we have a lot of techniques to avoid it, and one of them is dropout. So dropout is, I think, I have this theory, I have to check it, that some people were like sitting in a bar, having a few drinks, and like saying, our network is learning by heart those examples. It's too smart for those examples. Let's make it dumber. So that's the concept of dropout. Randomly choose a cell, put the probability on there to include this particular neuron in the training phase. So if it does not pass the threshold, we're just not looking at this neuron. So you could think like of applying weights 0 in this neuron. It's just, it does not forget what it has been taught so far. It's just not being taken into account in this particular iteration. Next time, it could be in, and those weights that were so far trained, they will still be there. And that's the key part. It's only happening in the training phase. Once you have your model that is built, once you want to check how well it performs on some examples, you cannot then randomly drop out your neurons. You have to have a deterministic answer. So only in the training phase, only when you're adjusting your parameters, your weights and biases, then you're applying dropout. When you're testing it, even when you're, like I'm checking the accuracy every 100 steps, even then I cannot use this dropout because it will be completely random. The result would not mean anything. So that's the concept. And my question is, I didn't put it as a separate layer, although TF layers package is putting as a separate layer. Is this a separate layer? So in my opinion, not, because again, it does not store any weights, does not have parameters to be adjusted. It just randomly applies some operations into my layer. So if we go back to Katacoda, let's see, how did it go? So it was now 97, and it was 97.28, 97.66. It is better, but you know, every percentage now is a gain. So I will just run it, because it will take some time on Dropout. Yeah?
So is the fact that the training batch accuracy was 99%, and then the test accuracy was 97%, is that an indication of it overfitting?
Yes, but also you need to think that we are actually training on batches, and we are evaluating only one batch. So we could be, yeah, or we could be lucky or could be unlucky on this particular batch. So it gives you some indication, but you shouldn't really rely on it. But if I was evaluating the whole training data set, even every 100 steps in a serious real-world problem, this will increase the time massively. But yeah, it's sometimes actually how you recognize it. Like you're saying, it's so good at recognizing my examples, right, during the training phase, but it's so rubbish when I put it in production. So just don't put it in production before you test it and put it into validation phase. So that's like 101 of machine learning. So yeah, dropout. Let's look at dropout. So everything else stays the same. I will just show you. The dropout. So this is the dropout. I have my hidden layer, and I have dropout. And I'm saying rate is 0.5, so we have half and half chance that our neuron will be dropped out. And I'm saying this is a training phase or not. So should drop is actually another placeholder that I'm saying that I will put the value when I'm evaluating it. So if you go to help, this is the thing. When I'm doing the training, I'm saying it shouldn't drop. If I'm going to testing it, I'm saying it shouldn't drop. If I'm training, it should drop. So depending on when you're using your neural network, you need to remember that if you're applying dropout, you need to tell your model which phase it is there. Because again, it's not magic. TensorFlow won't think for you. You have to think about your algorithm. So yeah, did we apply it? Well, I will come back to this later because we have to kind of finish.
Quick question.
Yeah.
Dropout. So up until this point, everything we've been training would be turning out the same result, right? It would have the same bias values. But now with dropout, I could actually have something where the second time I train on the exact same amount of data, is that random?
Yeah, good point. Good point. So dropout will put some kind of a probability there, right? So it's not deterministic anymore. There are a few points in like Adam or stochastic gradient descent or gradient descent. It sometimes takes some probability too. But yeah, pretty much it is kind of deterministic. And Dropout now is adding some randomness, specifically for this overfitting reason. That's why it's good once you have a model that works to save it. You have a model, you save it. You don't train it. That's one of the things. Another thing is real-world examples, real-world data sets. It will take you not hours, sometimes days to train. So you don't just want to do it every time you need to use it, right? So it's time for a summary. I talked to you a lot about deep learning. I could talk more because it's my favorite topic. And then we went through the classification task from this data set. We've built a very simple convolutional neural network. Convolutional neural networks are usually much more complex and have other spikes like ResNets, like inception. They actually have an inception mem that is an official mem for inception that comes from the film Inception. It's very cool. And we've built 1, 2, 3, 4, 5, 6, 7 layers, depending how you define it. So keep in touch. If there's anything I could help you with, don't hesitate to contact me. And I wish you a great rest of the day. And if you want to see what's the accuracy, I will put my slide in a second. 97.78, yay. So it did work. Dropout actually works. So thank you very much. Have a great conference.